So you've tried it yourself. I've also what you can also do in order to find out its factorability is to make a correlation plot and ggcorr plot, which you might come across also in your assignments, does that, and then you can get some really nice things like this. So if I go back, so what I've done here is I've called core plots, I've called dplyr. You need to have a matrix, and we want the absolutes of the correlations. We're not interested in the sign, so we're not interested if it's positive or negative. We just want the strength of the association. So you remember that we can use abs for absolutes, then calculate the correlation. And here I've just done it for the first 20, so that's the comma type thing. Turns out you don't need the comma, but I just put it in there. And then that will do a correlation matrix between the first 20 variables and just calculate absolutes. We then feed that to ggcorr plot, that matrix, and we tell it the order, and we tell it to move it to lower, and we tell it to make circles. And then you get something really nice like this, which gives you, there won't be any blue because there's no negative correlations, but we're looking for large pink or red or orange bubbles there, showing that there's lots of associations going on, which we can then reduce into a factor as.
What was that HC?
So that's just the color for this label, whether it should be positive or negative or something along those lines. So I think from the top of my head, otherwise we have to check out the manual. But I think that's the color labels for this. And we want it to be ordered in a certain way, so you could also have it going in the reverse way. From the top of my head, I would have to go back and look. But that's quite nice to see the size of the bubbles, and then hopefully you find lots of bubbles. So you might not want to do the entire KMO thing, but if you have this bubble thing, you can, hopefully it will be so clear that it hits you between the eyes that you see lots of bubbles, which are large, and that you can do factor analysis. Fortunately, more further terms, so you can click the link to read more. And so basically what we've been banging on about is factors, and factors are an underlying or related construct causing the observed variables. So we believe that intelligence is causing people's performance on Raven's progressive matrices, or people's personality dimensions are causing how they answer questions on being talkative or shy or lazy. And we can then find the best fitting factors, but they're not unique, and we can then try and rotate and try to get an interpretable solution. So you can show that once we have this initial set, so you might have recalled from your practical what you've done is that you first extract the factors and then you rotate them into a certain way, and then they become more interpretable, because you can think of it again as a space where you're rotating things and then trying to understand how the relationships align. And you can still think of that with 1 or 2 dimensions, but here we have 24 dimensions or something like that. But basically, it's a space which we try to rotate and then get scores to align, so to speak, and try to understand what's the clustering is going on between those variables, and if we can give some labels to those underlying clusters. Yeah? So factor loadings, that's the degree to which the variable is driven or caused by a factor. So we're looking for high loading, so that means that these questions contribute a lot to those latent constructs. And we can also have factor scores or factor weights. You can calculate them for every single item. So you can calculate them for every. So once we've done this thing and transformed it, we can give a weight to every single item and say, and this again you can think of spatial coordinates. You can say this is in this location, and it's in this position in terms of factor 1, and in this position factor 2, and in this position for factor 3. And then if we have 24 factors, you can't really do that anymore, but you can think of it as coordinates in a sort of system, in a solar system. And we can do that for every single item. We can sort of map out the coordinates where they're located, but we can also do that for people, and then we can say they're aligned in this way, in this space. Yeah, and that might be useful if we then later on use it. And then you should know a little bit about commonality and unicity, or a uniqueness, the extent to which the variability across participants in a variable is explained by the set of extracted variables. That's commonality. And uniqueness is 1 minus commonality. And again, some terminology should just be aware it exists, and your supervisor might ask you about it, or you might want to read about it more. And some of it will be printed in your outputs. And I won't discuss all of them, but you should know that they exist. Now let's do a basic factor analysis. So I used some type of rotation, and we begin usually by extracting a large number of factors and then trying to trim down the complexity. So usually we try to get a large number of factors first, and then we do some type of follow things to see if we should have extracted so many factors to begin with. But usually, well, that's the way I approach it. So it's a psych package, and then FA for factor analysis. We're going to store the results in FA. That's the data frame it's going to work with. You should make sure that it only has things which you want to go into the factor analysis, so no ID variables or gender or all sorts of other things. This is the number of factors we want to extract, so 8, like a large number of factors. The factor methods, there are different ways of extracting. Principal axis factoring is a common one, but min-res is another common one. You can read more about all those settings. Hopefully most of the time they will give you the same results, but sometimes they will give you different results. It's basically a way of computing the solution in this space, and you can do it in many different ways. And then we can rotate. As I said, the initial solution might be uninterpretable, but you can rotate it in different ways, and you can maximize the variance, or you can make sure factors are closer together. So there's varimax, promax, all sorts of other settings. And I've just gone with a common, which is called varimax. And again, you can read all the details in the manuals and all the different options. There's choice overload, as you'll be seeing. There's so many things you could pick from, and I've just gone with some common settings. And FA is FA because you can also use this FA command to extract principal components. And so we just tell it that we want factor analysis rather than principal component analysis. Okay, so we start with a large number of factors and we trim them down. We get a massive output, and so I install the sync where to put all the things which you recall from last time. So we put a text, and I'll open that now so you can sort of see what's going on rather than having to see through these things. There's lots of information there, and I won't run you through all the information, just the core. Let's see, FA output class text. Yeah. So here are eight different factors. They're ordered in terms of so factor 8 might be somewhere in the middle because it does better than the things after the rotation. So that's why it's not organized 1 to 8. You can then see the loading on all those different factors. We're looking for high scores there. So you can see, for example, that the first one was quite highly on distant, but not very high on talkative. So that might already point you to some direction as to what that factor might be. So lots of outputs. So you basically get loadings for all those. You get their commonalities and their unicities also per variable. So lots of information there. Information overloads will become clear when we go through it. But you're looking for high scores mostly for the factors, and mostly for the first couple of things you're trying to see where there's interesting things going on. So you could see distant, talkative, quiet, for example. So that is pointing to some things perhaps in terms of introversion, extroversion, yeah. So some things going on there. And you can see, for example, for the second factor, hardworking, it was high on hardworking, discipline, and it works negatively on lazy. So that sounds familiar, no? So it sounds like which personality traits? Conscientiousness, yeah. So it's pointing to those dimensions. So it seems that we're trying to, already we can see some type of structure emerging with the first factor being something along the lines of introversion, extroversion, and the second one being in the dimensions of conscientiousness. Yeah, that's what we would hope to find. So we're trying to look for high scores there and trying to see if there's some type of sensible thing going on there, which you can put a name to those factors. If that doesn't happen, then you've just amalgamated rubbish, or if you can't find a good term for it, then you might run into some problems. But wait, there's more output. So this is giving you the loadings, but also the variance explained by each factor. And we're looking for like, so the first factor explains 14%. The next one explains an additional 9%, 8%, and so they sum up. So you can have cumulative things, and it's also listed, twice. But so it's one is rescaled, so it goes to 100, as in a factor analysis, and the other one leaves. So this is actually the one you should report. All your factors combined explain 59%, those 8 factors. But if you think it's easier to explain from the subset, then you can get it going to 1. Yeah. It prints loads of things where I don't even know whether you should know about them, and I don't care too much about them. But the thing you care most about are fit indices, like mean square error of approximation, and the Tucker-Lewis index, and some there's more stuff. Basically, you can read through all the things, but mostly we care about the Tucker-Lewis index of reliability. We want that to be high, and we want this one to be low, below 0.06. And I'll come to you with some examples later. And those fit indices basically tell you how well those factors fit the model. You can also have the correlations of the scores with the factors. You can calculate all sorts of other things. You can have multiple R-scores, and you can have minimum correlations between all those different things. Lots of information. But I'll try and make it easier for the things you should really look for. So we've extracted too many factors, and now the question is, how many factors should we really have? And we'll come to that in a bit. So loads of outputs, some things to pick and choose from, but the initial thing you want to scan for is, can I interpret the first, because it will be in such a way that the first factors will always explain most of the variance, and they should be something meaningful and interpretive. So you should find some high loadings there, and they should be something you can put a name to it, as we put like introversion, extroversion, or conscientiousness, or openness to experience, or neuroticism, those type of things. Any questions at this stage? Okay, back to the slides. So occasionally I'll use syncs because it's just so much output and it won't fit on the slides, and you should also perhaps use syncs if you want to store away your output into a text file. Okay, we need to determine the number of factors, so how many hidden dimensions there are. Now in the case of personality, you might already know there should be big 5 or big 6, depending on who you follow. But suppose that we're agnostic and we're doing this for the first time. There's many different ways in which we could determine. There's 8 different suggestions as to how to do it. We can extract factors until the chi-square residual matrix is not significant. So you saw in the outputs, you saw chi-square is also printed for residual matrices. So you could do one with 6, one with 7, one with 8 until that is no longer significant. You can extract factors until the change in chi-square from factor to factor n+1 is not significant. That's another rule. You can extract factors until eigenvalues of the real data are less than corresponding eigenvalues of random data sets. And so basically the idea is that we can make random data sets from our data, or we can make random data sets like our data. And if we also get factor analysis in that noise, then that's not good. So we want to do that for the random data set and then for our own data set, and see where we still have a difference in where we're still extracting factors in our case, but not in a random data set. Yeah. And this is quite common, so I'll show you that. So the FA.parallel one is a quite common method. I come across those things fairly infrequently, so I'm not going to tell you too much about those. You can put the magnitude of eigenvalues, and then you can apply discrete test. So the discrete test you might have come across is this line with an elbow, where you're going to look for an elbow. So basically, you're going to look at the number. You plot all eigenvalues as light explain variance. The first one explains most, then the second one will explain less. And so the question is, when do you stop explaining additional variance? And then you will have an elbow in that graph, and you can visually look at it. I think it's quite difficult sometimes to see where you would put the elbow. Like So basically, what a sudden drop of eigenvalues analogous to the change in the slope seen when scrambling up the talus slope of a mountain and approaching your rock face. So you should think of it as a mountain where you're climbing up and where the elbow is, and like if it suddenly becomes a lot harder to climb up the elbow, then you put the cut point out there. Depending on where you're looking or if you're going down. Yeah, I'll have an example in a bit. You can another thing is just you extract as many as long as you can put labels to them. As long as you're able to explain them, then it's fine. You can use the very simple structure criterion, which is another way, VSS, and I'll show you that. And you can use Wayne's Villiser minimum average partial criterion, which is another way of doing it, and extracting principal components until eigenvalue is no longer larger than 1. So you stop at eigenvalue 1. That's usually, by now people agree that this is probably one of the worst criteria to do, because it's still quite common. That's known as the Kaiser criterion. The same Kaiser from the KMO type of test you do them. Choice overloads, yeah? So information overloads. Each has advantages and disadvantages. 8 also common is probably the worst. You can read more about here. And again, it's sort of more of an art in the sense that you look at different criteria and then you might settle on one. So it's not always hardcore science here, because lots of it is interpretability as to what the labels you are put on the things, where you put the cutoffs and where you put the measurements. What I haven't talked to you about in much detail is that here we have a nice case where most items seem to be doing well, but you might have some items which are unresponsive across all factors, and you would take those out and then redo it. So if you, in this initial setting, if you would find an item which does really, really badly and doesn't load on any of the factors, it doesn't in any meaningful way relate to all things, and that might happen. It might necessarily happen with personality, because most of the things can be realigned to one of those six dimensions, especially in our example. But then you would remove that item and do the exercise again. So you would filter through some of the items to see if you can also improve it. And so if you have items which are junk, which basically don't load clearly on certain components, you would consider removing those and then redoing it. Yeah, and then as long as you're transparent in every single step set, I removed those because item X doesn't always loads below 0.3 on all of the factors, then everybody will understand why you've taken out that item. Yeah. So this is a parallel plot, and so we've done the same thing. FA.parallel of data, and then we don't have to say how many factors it extracts, because it will go to as many as it will want. And so this is sort of the elbow thing I was talking to you about. So this is the line for eigenvalue is 1. So that Kaiser criterion. So you can see where it crosses the line. So you can have the actual data. So that's our blue triangles. The simulated data, and you can have resample data. So you can't really see the simulated data or the resample. You can see the resample data, but the simulated data are probably way below that. So just look at the resample. So that's if we just had junk. So you can see here it's still different from junk. So you would, in that case, perhaps say 5 different from junk. But if you this criterion, the question is whether you would still include that or exclude that. And then the question is where you put down this elbow. I would put it perhaps at 5 or 6, depending on where you think it goes flat. I think those are quite tricky things perhaps to determine. But that's sort of this. So this suggests 5 factors if you compare the red line to the blue triangles. So usually FA parallel is quite a good way of establishing things. Okay, in order to get the values, because you might not be able to see, so that triangle, is it just eigenvalues 1 or below? We can get all the FA values for all those 32 because it will just extract 32 factors. We'll continue going, and then you can see this one is still just above. Yeah, so it would also be 5 factors. Yeah, so first one has an eigenvalue of 6.5. 3.64, 2.38, 1.51, and then just above 1. So in this case, the Kaiser criterion and the parallel analysis would align and both say 5 factors. Yeah, you could, if you're really good, you would see it on the graph where it crosses the line, but sometimes it's easier to look at. Look here. So scree plot. So depending on where you put the elbow, 4 or 5, whether you think that's an elbow or not, and like basically, I think it's quite difficult perhaps to see sometimes. I'm not sure if people see different things in the graph where they put the elbow, but no. But basically, you could graphically look, and you could always just include that plot, and then people can make up their own minds, because this plot shows both the Kaiser criterion as well as the parallel test, as well as the scree elbow type of thing. And then you could say it could be 5, it could be 6. I'm going to settle on 5 because of this. Yeah. So the very simple structure test actually suggests 3 factors. So that's not very useful. And the map test says 6 factors. So sometimes you get different. That's what happens with real data. Not always it converges. So this is the plot from the very simple structure test. And unfortunately, you can't see it here, but it will then also print your conclusion for the map test. And that will say the map test is S. And so it's just VSS, F data, and again you have to say rotate, and here you have to say how many observations there are, how many cases, and how many factors you would like to evaluate. And there are cases where you can leave this behind, but it's always good to put in that for safety, because in principle, you can also just feed it a correlation matrix. You don't have to have the actual data sets. If you find somebody else who has published a thing and they've published their correlation matrix, you can also do factor analysis based on the correlations, because it's using the correlations. But then it has to know how many cases are behind the correlation matrix. So even if you don't have people's raw data from an article, you could reconstruct their factor scores from their correlation matrix if they reported it. And so you could sort of see that we wanted to be close to the line, and we see that we still improve. So in 1 factor, we improve. If we put in a 2nd factor, we still go a little bit up with a 3rd factor, but then the 3 and the 4 are really close, so it doesn't add that much more. So that's why here you would put it at 3. Yeah. So it's just basically, again, it's what you find big or small leaps. So some people might have stopped already there because they don't think there's a lot of improvement there. So it's to some degree it's that type of work. Yeah. But if you would have said that there's 8 factors here, then that was obviously wrong. Or if you would have said 1, you could still see there's quite some improvement. You go from 0.4 to 0.6. So it's not like in my assignment everything will go because he said everything will go, but there are some reasonable interpretations which everybody should be able to make. But the difference between 4 and 5 sometimes, or between 3 and 4, that's where people put the cutoff. And also when marking your assignment, I'll be slightly lenient in those type of things, but if you put like bigger ranges, then hopefully we can all agree that 4 is really close to 3 and it's not adding a lot more, and that 1 is too low that you could still improve on 1. Yeah. Now, conduct a factor analysis extracting a large number of factors for the data you have. Let's try and get 6 and store it somewhere, so put it in sync. And I would like you to discuss it with your neighbors, and then run a parallel analysis and discuss the outcome with your neighbors. So first, don't extract 8 because for you have only you have fewer items than I have, so I have 32 or something, and you have 24. So that's why you should extract 6. It should be relatively straightforward. It's just lines of code.